Okay, so one of the more popular types of physics experiments that people at well-funded universities often like to do is to take some subatomic particles and crash them into each other at high speeds. Examples of these experiments include pion-nucleon scattering, in which the victims are pions and nucleons, and pion photoproduction, where photons are fired at nucleons and pions come out. A lot of effort is also spent trying to model these reactions with quantum field theory, and this involves calculating things called scattering amplitudes, which, schematically at least, look something like this. And that can be a bit of a problem because it means that to get the amplitudes, we need to calculate and then add up an infinite number of, as it says, very complicated terms. As far as anybody can make out, adding all the terms is impossible, and so the amplitudes have to be approximated by dropping terms until they're reduced to something that, can be evaluated before one's scholarship runs out. In the literature, it's usual to actually retain an infinite number of terms, but a much smaller infinity that can be summed with integral equations. The problem with this is that it tends to lead to amplitudes that don't have the same symmetries as the full sum. In particular, pion-nucleon scattering amplitudes calculated this way won't have crossing symmetry, and pion photoproduction amplitudes probably won't have gauge invariance. Crossing symmetry is an important property of field theory itself, while gauge invariance is necessary in order for electromagnetic current to be conserved in a theoretically correct way. So there were two main aims to my project. The first was to derive a new set of equations for pion-nucleon scattering and photoproduction that are capable of both adding up an infinite number of terms and of maintaining crossing symmetry and gauge invariance while they do it. The second aim was to stick whatever equations we came up with into a computer and to get some numerical results out of them. First though, I'd just like to point out that even if we make a simplification and assume that pions and nucleons are point particles, the amplitude for pion-nucleon scattering will still look like something to be avoided at all costs. And so from now on, I'm going to A, assume that pions and nucleons are point particles, and B, represent horrible maths like this with some pretty pictures called Feynman diagrams. And in terms of the much nicer diagram notation, the amplitude will instead look like this. These solid lines represent functions of momentum that describe nucleons, while the dashed lines are the same things but for pions. Some order can be introduced to this infinite rabble of diagrams by dividing them up into two groups called reducible and irreducible, which are of interest because it turns out that if you know what the sum of all the irreducible terms is, you can shove them into this set of integral equations and calculate the sum of all the other diagrams. Predictably though, there's no known way of actually getting the sum of all the irreducibles, and so this group has to be approximated if these equations are to be of any practical use. And in the literature, they get used a lot. There, the irreducibles are replaced by a potential, which I'll call V, and this will either consist of a few low-order irreducible terms, or alternatively, a couple of fudge factors. If you stare at these equations for long enough, one of the conclusions that you'll eventually come to is that the amplitude t that you get by solving them will only contain a very limited class of Feynman diagrams. In fact, the only diagrams that t will have are those that can be formed by combining the potential and this uncrossed pions diagram. So things like that, and that, and that. A consequence of this very limited gene pool is that T won't have crossing symmetry. If it were crossing symmetric, then by definition, for every diagram contributing to it, there would have to be another that's the same, but with incoming and outgoing pion lines crossed over. But while T will include all the diagrams on the left of this table, their crossing symmetric partners with pion lines crossed over will be missing, because they can't be formed by combining the potential and that uncrossed pions diagram. T does, however, have the redeeming feature of unitarity, which means, in other words, that it's guaranteed to conserve probability. And it's because of this feature that these equations are a very popular way of describing pion-nucleon scattering. So popular, in fact, that I'll refer to them as being the standard description of this reaction. To take advantage of their unitarity, these equations are also often adapted to describe pion photoproduction, and this is done, essentially, by ripping off the incoming pions and replacing them with incoming photons, which I'll denote by a wiggly line or a gamma. Solving these equations then sums up an infinite number of gamma n to pion diagrams, although exactly which ones depends on what is chosen for the photoproduction potential V gamma. Ideally, this should be chosen so that the resulting amplitude has gauge invariance, but so far, whenever these equations have been used in the literature, V gamma hasn't been chosen in this way, simply because the authors haven't known how to. To get an idea of how one might go about constructing a gauge invariant amplitude, we should note that amplitudes that have this property satisfy the Ward-Takahashi identity. And this identity implies, more or less, that if you take any Feynman diagram at all, say, this one, then write down terms corresponding to all possible ways in which a photon could attach to it, and then add those terms up. The result will be gauge invariant. So in this diagram, a photon could, for example, attach here. So let's write that down. Or it could go here. So let's write that down. Or it could go here. Or if it was feeling really outlandish, it could even go just here. So let's write that down. Add the terms up, and the result is an amplitude that satisfies the Ward-Takahashi identity and is gauge invariant. This process that we just went through of attaching photons in all possible ways and then adding terms up is called gauging, and we say that the sum of these four diagrams is the gauged version of this one. Constructing an amplitude in this way will obviously become harder if we want it to have an infinite number of terms, because we'd have to take an infinite number of diagrams like this one and attach a photon to all possible places in all of them. In fact, it sounds impossible. But it turns out that if the equation diagrams to which we want to attach can be expressed in compact form by using an integral equation, the problem becomes doable. Doable, that is, if we use a technique called the gauging of equations method, which was developed by these people right in this very building, and then promptly ignored by almost everyone else, despite the fact that it's actually quite a major breakthrough. But I don't mind, because that meant that 15 years later I could base my project on it. The method is based on the observation that complete attachment of photons to all diagrams generated by an integral equation can be achieved by attaching to only a finite number of places in the integral equation itself. So with that in mind, we could construct a photoproduction amplitude by gauging this n to pi n integral equation, which is a slightly modified version of the one that appears in the standard description of pion scattering. By repeatedly plugging the left-hand side into the right-hand side, it's easy to verify that it contains an infinite number of diagrams, and hence places where a photon could attach. But if we just leave the equation as it is, there are only 4 possible places where a photon could go, and so gauging this equation takes us about 5 seconds, and we get this. Here I've used a superscript mu to indicate things that have been gauged. F mu is the infinite sum of gamma n to pi n diagrams that you get by gauging F. We don't actually know what that is yet, but to find out, we just need to solve this equation. Doing that effectively carries out the infinite attachment and summation automatically. Because this expression has a very similar form to the original integral equation for F, solving it turns out to be surprisingly straightforward, and after doing some algebra and solving and rearranging and finally carrying out an arcane procedure called the LSC reduction, we finally arrive at this result which I'll call the single gauging amplitude, or T1 for short. One thing we can notice about T1 is that it has the same form as the amplitudes that you get by solving the standard equations for photoproduction. And since these have unitarity, it immediately follows that T1 will as well. The big difference between T1 and the standard description is that here it's been specified exactly what the photoproduction potential V gamma needs to be in order to maintain gauge invariance. It should be this fairly complicated thing down the bottom. The standard equations, on the other hand, provide no clue as to what V gamma should be, so it's almost inevitable that amplitudes based on them won't have gauge invariance. In contrast, it doesn't take much algebra to show that T1 satisfies the Ward-Takahashi identity, and so the gauging of equations method solves for us the problem of how to construct photoproduction amplitudes with gauge invariance and unitarity. It so happens that it can also be used to obtain infinite length pion-to-pion amplitudes with crossing symmetry. The key to achieving crossing symmetry in a pion-nucleon scattering amplitude is for the incoming pions to attach to all the places where the outgoing ones do, and vice versa, which will be the case if the external pions attach to the other particles in all possible ways. That is, if they attach by gauging. So we could obtain a crossing symmetric amplitude by double gauging the infinite set of n-to-n diagrams generated by this integral equation, where by double gauging I mean that we'd first gauge them with an incoming pion and then take the result and gauge that with an outgoing pion. The gauging of equations method applies equally to the attachment of pions as to photons, and so we can use it here as well. Applying it to this equation twice, and then going through the usual algebra hoo-ha, we eventually arrive at this result, which I'll call the double gauging amplitude, or T2 for short. It's immediately apparent that T2 is crossing symmetric, since the diagrams that make it up come in crossing symmetric pairs. What it doesn't necessarily have is unitarity. In order to have this property, T2 would need to satisfy this unitarity relation. But what we actually find when we take the difference between T2 and its Hermitian conjugate is this. And so we have these pesky single gauging T1 amplitudes where there needs to be T2s. The T1 here is exactly the same as the T1 that we just derived for photoproduction, but with all the incoming photons replaced with pions. And since this will be a different quantity to T2, it would appear that unitarity is stuffed. On the other hand, T1 and T2 aren't that dissimilar. Both contain an infinite number of pion-to-pion diagrams, and in fact T2 will contain many, if not all, of the diagrams that T1 has. So this isn't really a situation of having oranges where there should be apples. Rather, if I was going to use a stupid fruit-based analogy, I'd probably liken it to a case of having, say, golden delicious apples where there should be Granny Smiths. And this may not be such a big problem, because if we go back to the load of horrible maths that I wrote at the start, I should point out that each of the integrals here are actually infinite in magnitude, and not because I've made a mistake. Non-convergent integrals are a notorious feature of quantum field theory, and there exist a number of methods of extracting meaningful results from them. One of these is called cutoff regularization, which is to multiply the integrands by functions of momentum called cutoff factors. These factors have a large momentum dependence in their denominators, and they force the integrals to converge. But because they're not based on any concrete theory, they also depend on a number of free parameters that need to be adjusted in order to fit experimental data. During this adjustment, it might be possible to carefully tune the parameters so that we end up with unusually yellow Granny Smiths and unusually green Golden Deliciouses, and hence achieve approximate unitarity. Or in more sensible language, I should say that it might be possible to achieve approximate unitarity, by carefully adjusting the cutoff factor parameters so that T1 and T2 coincide. And if you could do that, you'd have gone quite some way towards solving a very long-standing problem in quantum field theory, namely that of how to construct amplitudes that are both crossing symmetry and have unitarity. In order to find out whether achieving unitarity in this way is actually feasible or not, we'd need to do the numerical calculations and try to get this relationship working. A logical first step to that end would be to calculate T1, since it's a fair bit simpler than T2. In turn, a logical first step towards calculating T1 for pi n to pi n would be to calculate it for gamma n to pi n, since in the latter case, the numerical work could be checked by making sure that it satisfies the Ward-Takahashi identity. Once the gamma n to pi n calculation is working, it could be adapted to the case of pi n to pi n by replacing the incoming photons with pions. Another reason for calculating the photoproduction version of T1 first is that it has the novel feature of possessing both gauge invariance and unitarity, and so is capable of producing some quite interesting results in its own right. So for now, I'll talk about the calculation of this amplitude here. The first thing to say about calculating these diagrams is that it can be pretty tough. The main reason for this is that they contain a whole bunch of scary quadruple integrals. The diagram with the red circle around it, for instance, is actually this expression here, where I've censored the uglier bits by writing them as n. The integral isn't just over a single variable, but actually the three ordinary components of momentum k1, k2, k3, and also a zeroth component, k0, which is essentially an energy. Doing these integrals by hand on a piece of paper is well and truly out of the question, and so they need to be done numerically on a computer. But even that can be a real challenge, in part due to the factors in the square brackets, which are called propagators. When k0 is equal to one of these values, which are called poles, one of their denominators goes to 0 and the integrand blows up to infinity. Because the omegas are real, and the imaginary term I epsilon is extremely small, each of these poles are located extremely close to the k0 integration contour along the real axis, which would be okay if we were doing the integral by hand, but when a computer does an integral numerically, it can't tell the difference between poles that are close to a contour and poles that are sitting right on top of it. The real part of the nucleon propagator, for example, goes like this with k0, which sure looks like it goes to infinity, and if a computer tried to integrate over the top of these bumps, it would either produce a nonsensical number or a nonsensical error message, such as floating divide by 0. There are various ways of getting it across to a computer that the poles are not, in fact, on the real axis, but depending on the complexity of the Feynman diagrams, these can be difficult to apply. So one often resorts to an approximation to make the k0 integrals doable. One possibility is the spectator approach, which is to approximate one of the propagators with a Dirac delta function. These functions go to infinity at the same points on the real axis that the propagators become large, but are 0 everywhere else. The nice feature of this approximation is that it's consistent with special relativity. Applying the spectator approach to this propagator would involve making this replacement. Although the delta function spike is infinitely high, it's also infinitely thin and is set up so that the area underneath it is equal to 1. This results in the delta functions having this property and the k0 integral becoming very easy to do by hand. Trivial, in fact, because according to this, all we have to do is to replace all instances of k0 with omega n, and the approximated version of the integral I wrote up a few slides ago is this. With the k0 integral out the way, doing the remaining integrals numerically becomes much more feasible. A similar outcome could also have been obtained by approximating one of the other propagators instead, but we chose to target the nucleon one because, generally speaking, the spectator approach works best when it's applied to the heavier particles. We did the same thing to the other nucleon propagators in T1, and so reduced all the quadruple integrals in these diagrams down to comparatively simple triple ones. In the course of actually calculating these diagrams, we need to evaluate the blobs, which in the case of those marked F, G and T are given by the standard integral equations. To provide the necessary input to these equations, we first need to specify the cutoff factors, which we use to regularise the integrals, and the pi-n to pi-n potential. We chose the cutoff factors to look like this, which is a fairly standard choice in the literature, and here the capital lambdas are the adjustable parameters that need to be fit to experiment. For the potential, we chose a separable form rather than one consisting of Feynman diagrams. A separable potential is essentially just a function of momentum that, like the cutoff factors, depends on some free parameters. The reason for choosing such a potential is that it makes solving the integral equations much easier, and so reduces the amount of computing time needed to produce results. To set the adjustable parameters, which so far are unknown quantities, we put the cutoff factors and potential into the standard equations for pion-nucleon scattering, and then adjusted the parameters until these equations produced observables in reasonable agreement with experiment. The equation with the rectangle around it, for instance, contains all the information our model has about the absorption of pions by nucleons, and so should therefore produce the correct pi-n coupling constant, which is a number that determines the strength of the pion-nucleon interaction and whose value can be measured experimentally. Extracting the coupling constant from this equation is a matter of solving for f and then doing some algebra, and so this provides one condition to set the parameters to. Similarly, the pi-n to pi-n amplitude t should accurately describe the pion-nucleon scattering data. T actually contains a lot of subamplitudes because it depends not only on the energies of the particles, but also their charges and their angular momenta. The orbital angular momentum of the pion-nucleon system is labelled by a quantum number which I'll call L, and this can be any integer from 0 to infinity, although we only calculated t for L equals to 0 and L equals to 1 because at low energies most of the scattering happens in these two channels. T also depends on the total angular momentum, which is the sum of L and the spins of the particles. For these L's, J could be a half or 3 halves, but because we only wanted to calculate the photoproduction amplitude for the case of J being a half, we didn't bother trying to fit T to the J equals to 3 halves data. Finally, T depends on the total isospin quantum number, which essentially is just a cryptic way of describing the charges of the particles. In the pion-nucleon system, the isospin can be a half or 3 halves, and so to compare T with experiment, we extracted from it these 4 subamplitudes, which we then plugged into a simple formula that calculates observables called phase shifts. At first, we just guessed a set of parameters and obtained a coupling constant and phase shifts that are complete garbage. But then we got the computer to repeat the calculations about 20,000 times, and eventually it came up with a set of parameters that produced these results. The coupling constant now isn't that far off its experimental value of 13.5, and the phase shifts look fairly good too, at least over these energies. The x-axis shows the kinetic energies of the incoming pions before they crash into the nucleons, which in this case are assumed to be stationary. To go to higher energies, we'd need to take into account that the scattering starts to become inelastic, and since we haven't done that, we've restricted these graphs to looking at pion energies of less than 600 MeV. Since this fit to the pion data is reasonably good, we then proceeded to use the same set of parameters in a calculation of the photoproduction amplitude T1. Since the parameters are now fixed, the results that I'll show you from now on will be predictions of the data rather than just fits to it. A necessary input to T1 is the dressed photon-nucleon vertex given by the second of these equations. Just as we needed the pion to n equation to produce the correct coupling constant, this gamma n to n equation should accurately describe the absorption of photons by nucleons. To check that it does, we extracted from it observables called nucleon electromagnetic form factors. There are 4 of these numbers, with 2 each for protons and neutrons. The GM, or magnetic form factors, are equal to the magnetic moments of neutrons and protons, while the GE, or electric form factors, are equal to their charges. The GEs that we calculate are guaranteed to be equal to their experimental values of 0 and 1 only when the Ward-Takahashi identity is satisfied, and the fact that we've got 0 and 1 is a fairly clear indication that gauge invariance is being maintained. The GMs, on the other hand, aren't dictated to by Ward, Takahashi, or anybody else, and so our calculation could conceivably have obtained anything for these. What we got is a little bit off, but not too bad considering that we've treated the nucleons as being point particles. We also got fairly good results when we went ahead and calculated T1 itself, as shown in these graphs, which compare its real and imaginary parts with the data. The x-axes here show the energies of the incoming photons and start at 150 MeV because that's the smallest amount of energy that you need to kick a pion out of a nucleon. So all up, the results that we've got from the gauging equations are fairly encouraging, since given a simple model of pion-nucleon scattering, they've been able to predict the EM form factors and the photoproduction amplitudes, all with reasonable accuracy. However, our calculation does have a couple of aspects that certain picky thesis examiners might complain about. One of these is that although the EM form factors we calculated have about the right magnitudes, they correspond to nucleons that are the wrong size. So far, all the results I've shown have been for the case of on-shell photons, which are the sort that can be directly observed using equipment such as photon multipliers and eyeballs. A photon with momentum q vector and energy q0 is on shell if the difference between q0 squared and q vector squared vanishes. But in quantum field theory, there are also things called virtual photons that can have values of q squared other than 0. These photons can't be directly observed, but play a role in magnetic and electric interactions, and by doing various clever experiments, it's actually possible to measure the EM form factors corresponding to them. And so the GEs and GMs aren't just constants, but are actually functions of q squared, and at q squared equals to 0, they have both a magnitude and a slope. The slopes are important because they're interpreted as being closely related to the radii of protons and neutrons. But when we calculated the form factors over a range of q squared values, we found that while the GM slopes aren't too bad, the GEs go off in completely the wrong directions. So that's one problem. The other problem is to do with the pole diagram in T1. One of the properties of field theory amplitudes is that they have poles when the energy of the incoming particles is that of a bound state. Because nucleons absorb photons, the bound state of a photon and a nucleon is just a nucleon, and so photoproduction amplitudes have poles when their energy is equal to the nucleon mass. The part of T1 that has this pole is the first diagram, and in particular the blob in the middle of it, which is called the dress nucleon propagator. To make it clear that the dress propagator has this pole, the diagrams that make it up can be rewritten into this form. When the energy E is equal to the nucleon mass Mn, the first term blows up and the rest go to zero. In exact field theory, the coefficient of the explosive term, which I've called Z2, is always a number between 0 and 1, and for this reason it's often interpreted as being a probability. But when we calculated Z2, we got 1.3, which obviously isn't consistent with this interpretation. In order for Z2 to be between 0 and 1, the derivative of that pion loop diagram needs to be negative. It turns out that this will always be the case if the loop diagram is well defined for all possible values of E except those which lie along these red lines, which are called cuts. For these values of E, the loop diagram should blow up to infinity. As derived from field theory, the diagram does indeed have this structure. Unfortunately, the cutoff factors that we introduced to regularise the integrals change the structure by contributing an extra pole to each of the four quadrants. What's worse is that the spectator approach causes the cut on the left to shrink and then move closer to the origin. Bing! All this vandalism of the loop diagram structure allows its derivative to be positive or negative, and hence for Z2 to be virtually anything. If we'd got lucky, we might have got Z2 to be between 0 and 1 anyway, but we found that in order to send Z2 back to its correct range, we had to come up with a modified version of the spectator approach. So far, we've implemented it by approximating the nucleon propagators with delta functions. Another possibility is to approximate the anti-pion propagators instead. Doing that causes the loop diagram structure to change to this. And so, just opposite to what happened before, the cut on the left remains unchanged and the cut on the right does the shrinking instead. And so, if we were to write the loop diagram as the sum of two loops, and then approximate the nucleon propagator in one and the anti-pion propagator in the other, then the result would have both the cuts that the original unapproximated diagram had. That is, one from big M to infinity and another one from minus big M to minus infinity. You'd also expect it to have two extra shrunk cuts in the middle, since both the approximated diagrams individually have cuts here. However, it so happens that when E is equal to one of the values along the yellow lines, that the two approximated diagrams are equal in magnitude and opposite in sign, and so cancel each other out. This means that the extra cuts don't arise, and this modified spectator approach doesn't change the cut structure. And so we figured that it would be a good idea to actually use it in calculating the loop diagram, and hence Z2. For consistency, we also adopted it everywhere else in our calculations, and so replaced every other integral with the sum of itself and a clone, and then approximated the nucleon propagator in one and the anti-pion propagator in the other. It's less clear, at least to us, how to get rid of the cutoff factor poles, but these don't seem to matter quite so much, because when we used the modified spectator approach and got the computer to refit the parameters, we obtained phase shifts and a coupling constant that are fairly reasonable, and most happily of all, a Z2 between 0 and 1, notwithstanding the presence of the cutoff factor poles. Another favourable outcome of using the modified spectator approach is that the EM form factors now will go in the right directions, although their slopes at q squared equals to 0 still aren't quite right, and the magnitudes of the GMs aren't that great either. There are, on the other hand, a lot of good descriptions of the EM form factors in the literature. Those that, like ours, treat the nucleons as point particles usually take the view that photons, when in the process of being absorbed, turn into particles called vector mesons. In other words, they say that if we have a nucleon and an incoming photon, then the first thing that happens is that the photon turns into a vector meson, and this is the thing that gets absorbed. This theory is called vector meson dominance, or VMD, because diagrams like this one make a large contribution to the form factors. In contrast, we've assumed that nucleons just absorb photons as they are, and that the main contribution to the form factors comes from pion-loop diagrams. Although our photon-nucleon vertex actually has an infinite number of pion loops, whereas VMD models only have a small number, if any at all. We kind of thought that the large numbers of loop diagrams that we have might negate the need for the vector mesons, but this apparently isn't the case. And so to fix the form factors, we replaced the first term in this vertex with a vector meson exchange diagram. This contains masses and coupling constants that we adjusted in order to fit the data. Not surprisingly, this fixed the form factors, and they ended up looking pretty well perfect. Happily, the vector meson term also improved our prediction of the photoproduction amplitudes. When we left it out of the equations for T1 and used the modified spectator approach, they produced these results, which don't look that bad. Introducing the vector meson term, though, actually caused some of these curves to move closer to the data, thus validating, at least to a certain extent, our decision to use it in fitting the form factors. The vector meson term was introduced to our equations in a fairly ad hoc sort of a way, but the fact that it subsequently helps to predict other data gives it at least some theoretical basis. And so, in summary, we can say that given a simple model of pion-nucleon scattering, the gauging equations have been able to describe the magnitudes and the slopes of the EM form factors and predict the photoproduction data, all with reasonable accuracy. It's interesting to compare these results to what you get from the standard description of photoproduction. A good model to compare with is that of Gross and Surya, who calculated an amplitude from these equations. Like us, Gross and Surya simplified all the integrals by using the spectator approach and chose a separable pion to pion potential. They also added some extra diagrams onto this amplitude that allow it to approximately satisfy the Ward-Takahashi identity and so to have approximate gauge invariance. Despite this, they found that their amplitude actually gives results that are fairly poor. The dotted lines in these graphs are what they initially calculated, and they found that to get to the solid lines, they had to add some extra vector meson exchange diagrams with free parameters. The fact that our T1 has been able to predict this data without needing the extra parameterization would appear to indicate the importance of maintaining gauge invariance in the theoretically correct way. That is, by ensuring that the photons attach to the other particles in all possible ways, which is of course how we derived T1. More specifically, we derived T1 by attaching photons everywhere to this n to pi n integral equation. Now, I don't know if this is appropriate or not, or indeed if this is even going to work, but I reckon that T1 and the gauging of equations method that we use to derive it are almost worth singing about. So I'd now like to pay homage to them with a song that might almost be worth listening to, although probably not. Lots of people have tried to construct photoproduction amplitudes, but gauge invariance always ends up being screwed because the photons need to attach in every possible way to an infinite sum of terms, and that's too hard, they say. But the gauging of equations method has the problem solved and gave us infinite attachment with only stuff or work involved. And they attached everywhere, man, to the diagrams there, man. No single place was spared, man. I doubt you really care, man, but they attached everywhere. They attach to the left, to the right, to the top, to the bottom, to the middle of the first diagram, to the left, to the right, to the top, to the bottom, to the middle of the second diagram, to the left, to the right, to the top, to the bottom, to the middle, to the potential, to the vertex, to the V, to the F, to the one with the two loops and the bit coming out of the square, and yeah, and so on to infinity. But to make sure we get over here by 2 o'clock, let me just skip to the end of the song and say of the photons that they attached everywhere. And that's how we derived T1. We also attached pions everywhere to an infinite set of n to n diagrams, and in doing so, derived an amplitude for pion-nucleon scattering with crossing symmetry. It turned out that this amplitude only has unitarity if it coincides with the pi-n to pi-n version of T1. And so the next thing we would like to do is to repeat the T1 calculations that we've already done, but with the incoming photons replaced with pions. Then we would like to actually calculate the crossing symmetric amplitude and try to get its unitarity happening. Because if we can do that, we then have a model of the pion-nucleon photon system with crossing symmetry, gauge invariance, and unitarity. Unfortunately, I didn't get time to do any of that, and so today we'll just have to settle for gauge invariance and unitarity, and that's it.